Hello. In this video, we are going to derive the sigma molecular orbitals of NH₃, ammonia, using the projection operator method. As a first step, we have sketched the molecular structure of ammonia, and we have put it in such a way that the x-axis is going left and right, the y-axis is up and down, and the z-axis, which is also the axis of the C3 high order rotation axis, is coming out of the whiteboard and perpendicular to it. We recognize that ammonia belongs to the point group C3V, and we begin to sketch out the table that we're going to need to set up a reducible representation for the sigma molecular orbitals of ammonia. We seek to find the linear combination of group orbitals, that is the orbitals on the external hydrogen atoms, the 1s orbitals of hydrogen, that have the symmetry to combine with atomic orbitals on the central nitrogen atom. So let's label the 1s orbitals of hydrogen as S1, S2, and S3. What we want to do now is to develop a reducible representation for the sigma orbitals. So this is gamma orbitals that don't move. So you just want to see which orbitals don't move under a particular symmetry class of the point group. So under the identity, all three of the sigma orbitals stay where they are. So this character becomes a 3. Under the C3 operation, S1 goes to S2, S2 goes to S3, S3 goes to S1, so none of the orbitals stays put, so our character here is going to be a 0. If we take the vertical mirrors, so one of the vertical mirrors is going perpendicular to the whiteboard along the y-axis, we see that S2 gets reflected as S3, S3 gets reflected as 2, but S1 gets reflected to itself. Since it stays put, the character for the reducible representation here is going to be a 1. Our next step is to reduce the reducible representation gamma orbs into a linear combination of irreducible representations from the point group C3V. The first such irreducible representation is A1. And in our reduction formula, the first step is to have a factor 1 over the order of the group. Since there are 1 plus 2 plus 3 equals 6 symmetry operations for C3V, the order of the group is 6. And our factor in front here is going to be 1/6. Then recall, the first factor in each term is going to be the number of operations in the class, which for E is going to be 1. The character of the reducible representation is a 3. And then we have the character from the irreducible representation, A1, in C3V, and that character is a 1. Now, to expedite our work, we recognize that the character for the reducible representation for the C3 class is 0. Since one of the factors in the middle term here for C3 is a 0, it doesn't matter what the other terms are going to be because anything times 0 is equal to 0. So we just end up with a 0 for each of these terms with regard to C3. Literally, this is 2 times 0 times 1. Then for our third class, there are 3 operations in the class. So we have a 3, and that's the red 3 up there. Our character from the reducible representation, we have in blue, that is a 1. And then the character from the character table for the irreducible representation, A1, is a 1. So here we have 3 plus 3 divided by 6 is equal to 1. So that tells us that inside gamma orbs, there is one A1 irreducible representation. Next, we look for the A2 irreducible representation. Again, we start off with 1/6 because 6 is the order of the group. For E, there's one operation in the group, in the class. The character from the reducible representation is A3. And we've had that color-coded there. And then the character from the irreducible representation, A2 in C3V, is a 1. Similarly, since we have a character of 0, we end up with a 0 for the C3 class. Then for the sigma V class, the final class, we have 3 operations in the class. The character of the reducible representation is A1. And the character from the irreducible representation for A2 is a -1. So here we have 3 minus 3 is 0. So there are no A2 irreducible representations included in gamma orbs. The third and final irreducible representation in the point group C3V is E. So again, we have 1/6. The number of operations in the class for E is 1. The character from the reducible representation is 3. And now the character from the irreducible representation E in C3V. We recognize E is a doubly degenerate representation, so its character is a +2. For C3, again, the middle term ends up being a 0. And then for sigma V, the number of operations in the class is 3. The character of the reducible representation is a +1. And then the character from the character table for the irreducible representation E is a 0. So here we have 1/6 of 6 is equal to 1. So therefore, we can write gamma orbs as a linear combination of irreducible representations. We have 1A1 and 1E. Now notice that if we start off with 3 atomic orbitals, we will end up with 3 molecular orbitals. And we notice that we have 3 here because we have one singly a non-degenerate representation and one doubly degenerate representation. So this counts as 2 molecular orbitals, and this is the third. So we have the correct number of molecular orbitals by reduction of the reducible representation, gamma orbs. The next step is to determine what these particular molecular orbitals look like using projection operators. So we make a chart, but in this chart we need one column for each symmetry operation, not just one column for each class. So we have E, and then we have 2 C3s. So we usually write this as C3 for the first, and then C3 squared for the second. So these are the 2 C3s that are in the class in C3V. And then we have 3 separate vertical mirrors, sigma V. Next, we take a representative atomic orbital, S1 here, and we see what happens to that under the various symmetry operations of the point group. So we notice under the identity, S1 is just S1. If we do a C3 on S1, S1 gets turned into S2. If we do C3 and then C3 again, S1 becomes S3. If we take this particular sigma V mirror plane, it reflects S1 into itself. If we take this particular mirror plane, it takes S1 into S3. I'll put that there, just put it in order. And if we put this particular mirror plane, it turns S1 into S2. there's no significance to the order other than it makes it nice to have 1, 2, 3, 1, 2, 3. Next, to see what these particular orbitals were going to look like, first we need to write down the characters from the irreducible representation A1, because we know we have an A1 molecular orbital. And we know that the characters from the irreducible representation for A1 are all positive ones because A1 is the totally symmetric representation. So we multiply the character in the second row times the term in the first row, and we get S1 plus S2 plus S3 plus S1 plus S2 plus S3, and we can condense this as S1 plus S2 plus S3. Notice that if you know about normalization, for brevity, we're omitting the normalization constants, just to make it more easy to see what the molecular orbitals look like without having the complication of additional factors in front. So this is the A1 molecular orbital. And we'll see in a bit what that actually looks like. So our second terms that we have to figure out what the E molecular orbitals look like. So again, we need to continue our chart. And we have a column for each of the operations in the group. And we can just copy down the first row. This does not change. So we have what happens to S1, S1, S2, S3, S1, S2, and S3. So now we want to write down the characters for the E doubly degenerate representation. And we notice by looking at the character table that the character for E is a +2. The character for each of the C3s, so for anything in this C3 class, the character is going to be -1. So make sure we put -1 for both of these. And we also notice that the characters for the sigma V's are all equal to 0. So now again, we do the same thing we did for A1. We multiply the characters in the second row times the terms in the first row. And we get 2S1 minus S2 minus S3. And this is one of the two E molecular orbitals. Now we've seen that one of the two doubly degenerate E molecular orbitals can be described as 2S1 minus S2 minus S3. So that is, now we need to find the other member of the pair. We need a two-step procedure to do this. So the first step is to take this particular expression and perform a C3 operation on this expression. The reason why we do this is the cause of degeneracy in the first place in a point group is having a high order rotation axis of order 3 or greater. So it's the fact that we have a C3 high order rotation axis for this molecule that leads to degeneracy in the first place. So our technique is to perform a C3 operation on this expression. And we do it term by term, and we notice that the rotation operators are linear. So if we have a coefficient in front, we can simply pull the coefficient in front of the C3 operator. So if I want to do a C3 on 2S1, that is exactly equivalent to 2 times the C3 of S1. So we notice that if I have S1 and I do a C3 operation on it, it turns S1 into S2. So therefore, if I do a C3 on 2S1, that turns it into 2S2. So our 2S1 becomes 2S2. And I'm going to write the effect on the next line. Similarly, if I do a C3 on S2, it turns S2 into S3. So if I do a C3 on minus S2, it becomes minus S3. Last but not least, for S3, if I do a C3 on S3, S3 becomes S1. So if I do a C3 on minus S3, it becomes minus S1. So what we've done so far is we've performed a C3 operation on our expression for the first molecular orbital. So we might suspect that this second term that we've written on the second line is the other member of the doubly degenerate molecular orbital. It turns out that is not true. And in fact, this particular expression is the same as the expression above it, simply shifting the labels for S1, S2, and S3. That's the bad news. The good news is if we subtract this expression from the first expression, it will actually give us the other member of the doubly degenerate pair. So we need to subtract the term on the second line from the first line. And if we do that, we get the expression 3s1 minus 3s2, which is the same as s1 minus s2. So that is the other member of the E doubly degenerate representation. So, in summary, by expression, A1 is S1 plus S2 plus S3. For E, we have two expressions. We have 2S1 minus S2 minus S3, and we have S1 minus S2. The final step of the derivation is to draw the group orbital combinations and determine which atomic orbitals on nitrogen have the proper symmetry to interact with the group orbitals. So, if we start off with A1, we notice that we have S1 plus S2 plus S3. The fact that they all have positive coefficients tells us that they all have exactly the same phase. So we can sketch this molecular orbital as follows. Since all the hydrogens are white circles, they all have exactly the same phase. So now we need to determine which atomic orbitals on nitrogen have the proper symmetry to combine with the hydrogen group orbitals. And we notice that the 2s orbital on nitrogen has exactly the right symmetry. So we can make the A1 molecular orbital combination by combining the S1 plus S2 plus S3 of the hydrogen atoms with the 2s orbital of nitrogen. For E, we have two combinations. Our first combination is 2s1. So since it's positive, we'll draw that as a large white circle. Minus S2, minus we draw as a filled-in circle, has an opposite phase. Minus S3, which is the same size as S2 and the same phase as it because they're both negative. So here we have 2s1 minus S2 minus S3. And we need to know which orbitals on nitrogen have the proper symmetry. So we recognize that we see positive at this end and negative at the other end along the y-axis. So if we combine the 2py orbital of nitrogen with this linear combination of group orbitals on hydrogen, we can make a sigma orbital. We see that at this end we have bonding with bonding, same phase, so that's a bonding interaction. At this end we have negative phase, negative phase, so these are all the same phase. That's also a bonding interaction. And we notice, running through the molecule, it goes from positive through 0 to negative, so we have exactly one node. Up here, everything has the same phase. There is no point at which the wave function goes from positive through 0 to negative, so A1 has no nodes. We see that E, the first E here, has one node. Let's look at the other E combination. We have S1 minus S2. So now we need a combination on atomic orbital on nitrogen that will match this combination. So we know that we have to have a p orbital with a positive phase to combine with this hydrogen atom, but a negative phase to combine with this hydrogen atom. So this particular orbital we have here is 2px for the other member of E. The last atomic orbital that we have on nitrogen doesn't have proper symmetry to combine with any of the group orbitals. So that is going to be the 2pz orbital, and that is going to be the orbital that has the lone pair, that is a lone pair for ammonia. For our last step, we can make a relative energy diagram for these particular molecular orbitals. Since A1 is an all bonding combination with no nodes, that is going to be the lowest in energy. Next we have the doubly degenerate E orbitals. So they have exactly the same energy because that's what degenerate means. So we have A1, the two E's, and then the highest energy is simply going to be an atomic orbital that remains on nitrogen. That is the 2pz orbital. Now, we have, for ammonia, we have 8 valence electrons, and we can approach molecular orbitals in much the same way that we approached atomic orbitals. We can use the Aufbau principle, and we can use Hund's rule. So we notice that the first 2 electrons go in A1. We have 4 more electrons to fill up the E molecular orbitals. So this is 6 valence electrons. And the last 2 valence electrons go in an orbital that is an atomic orbital that sits entirely on nitrogen. So this is the lone pair, the very important lone pair of nitrogen in ammonia, which makes ammonia such a potent base. Thank you very much for your attention. Have a good one.